All right. Almost done. So close. So what are we doing? Last week, when I just made you watch a video, we were talking about Newton-Euler. Now we are on to work energy and momentum for rigid bodies. And those are the two topics for this week. And then a week from today, we'll talk review for the final, and then we're done. So it is very, very close. You should be excited. All right. So, yeah. Today we'll take kind of a little trip down memory lane back to Chapter 4 where we talked about work energy. But now we'll have essentially one more term that we need to carry along that accounts for that rotation. So if you liked what we did in Chapter 4, hey, I think you're going to like what we're doing now. It's not a whole lot more difficult. If work energy confused you a little bit the first time, here's your chance at redemption. Learn it again. And that same story will be true when we get together on Thursday, where we'll talk momentum, particularly angular momentum. We really sped through that in Chapter 5. Because I told you it wasn't on the exam, so therefore none of you guys studied it. Now we'll work on it. And it makes, I think, a little bit more sense with rigid bodies. So we'll talk rigid bodies. We'll talk about how you can also include particles, and it'll all work out. So, all right, let's go. Work energy. So what do we do with work energy before? We said we had Newton's second law, F equals ma. We took this whole thing and we integrated it over the distance. All right. So if we kind of work that through, we had the integral of f dotted with dr. We called this part work. Gave it the u variable. The other side, m acceleration dot dr. We played with this a little bit, but it was a kinetic energy t. You had half m v2 squared minus half m v1 squared. So all we did, we started with f equals ma. We integrated it over the distance. And we got something that was pretty nice to work with. So these problems were good for speed and position. And the way that we ended up using all this together was we looked at that work energy expression. So we had, hey, what's my kinetic energy at state 1 plus, from this work term, we pulled out conservative forces. I had potential. So I had potential at state 1 from gravity. If you wanted, we also had potential at state 1 from springs, plus my work between states 1 and 2, non-conservative. For us, this was typically friction, energy we lost from dragging a box along, or maybe we had an external push or pull force that we needed to account for. This was equal to kinetic energy at state 2, half mv2 squared, plus our potentials at state 2. So if we had gravity to deal with, or if we had spring potential to deal with. And what was really nice about this setup for work energy is that, hey, you write your base equation, you got an idea of what state 1 looks like, you got an idea of what state 2 looks like. All we were doing was filling in the blanks. And the problems kind of solved themselves fairly easy. Remember this work between states 1 and state 2, that could get a little messy. It was an integral over the distance. So our work integral from state 1 to state 2 of all those non-conservative forces dotted with displacements. Sometimes that was tricky. Sometimes, if your forces were constant over a distance, that integral really just became a multiplication of force times distance, if these forces were constant. Remember that we got a little dot product in here, so it was only the forces in the direction of motion that you cared about. Otherwise, what we got when we made this dot product of two vectors is a scalar equation. So we had half mv squared. We didn't have to worry about the direction of v. mgh, well, we had to pick a datum and figure out if we're going up or down, but again, our work energy, scalar equation, life was pretty good. Everything seemed to work out. All right, so now, imagine we've got this flywheel spinning around and around and around. The way we would have taken care of this for a particle, we'd said, hey, if I was modeling this flywheel as a particle, I'd put all its mass at its center of gravity, CG. And then, for the particles, we said, oh, well, kinetic energy is half mv squared. If you imagine that this thing is spinning along the z-axis, which is fixed, our old method would say t is equal to half m v squared. Well, at the CG, the velocity would be 0, because it's pinned along that axis that it's spinning about. So we'd say, hey, we've got no kinetic energy from this thing spinning. Like intuitively, doesn't feel right. The example I always use is, imagine this was like your bicycle wheel that you spun up real fast, and as your bike's lifted off the ground, and you stuck your hand in there, and it shredded your fingers off. You're like, well, that was some energy that ripped my fingers off, right? Clearly, just because the center of mass isn't going somewhere, doesn't mean that we don't have kinetic energy. So, the way we're going to think of this is that for this pie plate or disk or whatever's rotating, we'll look at each little incremental mass, dm. And we can think that, hey, this energy is going to be the sum of the motion of all of these little masses, all their little velocities. So if t is half m v squared, maybe we can think of an incremental energy is half dm times the velocity of each one of these little guys squared. And then if we wanted the kinetic energy over the whole body, we're just going to integrate this over all of those little masses until we get an answer. And we could do that, but it's the last week of class, and the derivation is not that fun. Sleepy. So we'll fast forward. If we integrated this over mass, we would get something, our kinetic energy term. We would have something that looks like we had before. Half m v squared. And I'm going to put a little g there. Half mass times the velocity at the center of gravity squared, plus, now we're getting the rotation part, half moment of inertia about g omega squared. So we can think of this first part, it's our translation, and the second part is our rotation. So now for these rigid bodies, we're kind of developing a way to account for kinetic energy if that body isn't moving anywhere, but it is actually rotating. So That's the only thing new. You got a whole new chapter, and all you learned was one new thing. That, hey, we're going to account for kinetic energy by half moment of inertia about g times omega squared. Everything else, pretty much the same. So, again, thing to keep in mind, that's the moment of inertia about g, about our center of gravity. We'll look at a special case. If we've got like a pinned body, which is what we're showing on the screen here, it can be any old pinned body, but our body's pinned at point O, and I've got this pendulum over here. And maybe this pendulum is, it's got a rigid bar and a disc at the end. If we're trying to find the energy for this, hey, I got to find the translation and the rotational part. If I just look at this big guy here, I have some disk at A. Its motion is linked. The rotation of this body, because it's pinned, and its translation, the fact that it's riding that circular path, they're not two independent variables. V and omega are coupled because I'm riding the circular path. Now, if we jump back a slide, where I've got this random blob may be, maybe it's like a potato. I launched out of a potato gun. It's flying at some velocity, and it's also tumbling, flipping back and forth. All right, that's two different things that aren't necessarily linked together. Like, hey, how fast is it translating, and how fast is it rotating? There's no way to relate omega to V. They're just two things that are happening. It's doing both. So that's why I need two terms there. But here, this becomes a little easier. Here, my velocity of this disk, so my velocity of g here, my center of gravity of the disk, is related to omega, right? So this is just omega times r, where r is my distance away. So if we put that in, t is equal to half m vg squared, that's omega r squared, plus half ig omega squared. A lot of the terms are the same. Got a half out front for both of them. Got an omega squared on the back end for both of them. And in the middle, from this first term, I've got a mr squared. And from the second term, I got an ig. Well, what is this? This is like our old friend. This is just a parallel axis theorem. So this is telling me that my moment of inertia about my pinned location is my moment of inertia about, in this case, the disk, about its CG, plus our offset, mr squared. So if we have a case where we have a fixed axis rotation, then our kinetic energy is simply half I sub O omega squared. If we know our translational path, because it's on a fixed axis, hey, I don't have to carry along both of these terms anymore, because I can relate the velocity of my center of gravity to its angular velocity. Life is easy then. One term if something's pinned and rotating about that point. All right, this slide just summarizes that. Top one, always true. Kinetic energy of a rigid body. Hey, figure out what its translation of its center of gravity is, figure out what its rotation is, or if I'm lucky enough to have this thing fixed, then I can relate the velocity of the CG to its angular velocity, and this becomes easier. I just have one term then. At the bottom, sneaking this in here, note that point O could be the instantaneous center. Hey, instantaneous center can act like the point at which this rigid body is rotating purely about. So maybe an example, if I've got a ladder leaning up against a wall, and it starts sliding down, and we want to figure out the kinetic energy at some location as it's falling down. So as this thing is falling, my ladder comes like this, goes, whew. It's doing some rotation, some translation. But if I can figure out the instantaneous center, assuming it stays touching this wall and touching the ground, my velocity at the top, my velocity at the bottom, and then to find our instantaneous center, those contact points go perpendicular to our velocities. Okay, that's my IC. So at this instant in time, it looks as if this rigid body is rotating about our instantaneous center. So for us, maybe this is my CG here. We want to reference everything with respect to our instantaneous center. So we would have kinetic energy half I with respect to the CG times omega squared. Maybe that's some distance d. Our CG, this isn't CG, this is IC, I'm sorry. So my moment of inertia with respect to the instantaneous center is going to be equal to my moment of inertia with respect to the CG plus the parallel axis shift, mass times the distance squared. So for us, everything is really going to operate the same way we did before. This is the new part, just tracking rotations. All right, let's crank us through a little example. So I've got an L-shaped bar consisting of two uniform bars, each of length L and mass M. All right, so the same bar. For 1 point, determine the mass moment of inertia of the bar about the pin at O in terms of M and L. And for a bonus point, calculate the kinetic energy when it's rotating at 2 radians per second, given the mass is 1 kilogram and the length is 1 kilogram. All right, so we're trying to find kinetic energy of this system. The first step is telling us, hey, go and figure out IO. Find our moment of inertia of this composite system about point O. Because then our second step, kinetic energy, is just going to be half IO omega squared. Right? So if I want to find the total moment of inertia of the whole system about 0.0 first, that's the hard part. Kinetic energy is easy because it's pinned. All right. So the hard part, taking us back to statics. What's my moment of inertia about O? Two bars, bar 1 and bar 2. I'll draw them over here. They're both length L. So my moments of inertia, I got the moment of inertia of bar 1 about O plus the moment of inertia of bar 2 about O. All right, bar 1, that's a thin rod. So I could do moment of inertia of this thin rod about its CG plus a parallel axis shift. Or I can say, I remember that. A thin rod about its endpoint is 1/3 ml squared. This is a rod about endpoint. It's not in our book, but we use it so often that I think we can remember that one. Okay. But bar 2, I got to move that one a ways. So how far do I got to move it? I got to move it all here to D. Got to move this guy all the way back home. So for this one, 1/12 ml squared plus the parallel axis shift. So this is about its CG. And its parallel axis shift is mass times distance squared. Well, if this part of the triangle is L, this part is L over 2. The length is the square root, L squared plus L over 2 squared. And it's mass times that length squared. So that actually works out pretty nice for us. I got a square root of a square, or a square of a square root. So IO is 1/3 ml squared plus 1/12 ml squared plus m times L squared plus L squared over 4, or 5/4 L squared. M's and L's everywhere. This just becomes 5/3 ml squared. So really want to get you guys comfortable with taking a system, multiple pieces, putting their moments of inertia together, and then finding them with respect to a single point. So this is what this is all about. Hey, we did the first one kind of fast. Moment of inertia of bar 1 about 0.0. Instead of doing the parallel axis shift, we said, hey, we know what that is. It's 1/3. The second one, kind of did the full way. Moment of inertia about its CG plus its parallel axis shift back to O. Now the easy part, what's the kinetic energy? T is half IO omega squared. So for us, half IO was 5/3. Mass is a kg. L is a meter. Omega was 2 radians per second. All right. 2 squared divided by 2 is a half. 10/3. Let's look at the units. kg meter squared per second squared. Or kilogram meter per second squared, that's a Newton, and there's another Newton meter. So this is also Newton meters. Newton meters, hey, that's our work unit, right? Or our energy unit. So life is good here. All right, to keep harping on this problem, we could have done it a different way. We didn't have to use energy about 0.0 that in fact it was pinned. We could have said that our kinetic energy term could have said our kinetic energy term was the combination of the translation and the rotation. This could have been kinetic energy of bar 1 plus the kinetic energy of bar 2. I don't really love that notation, but so bar 1, half m1 v1 squared plus half I of g1 omega squared, plus the same thing for bar 2. Half m2 v2 squared plus half ig2 omega squared. So instead of thinking about these guys as being pinned about O and simplifying this as one rigid body, we can just take that energy from both these and add it along. And you're free to do whatever your brain thinks is easier, because parts of this are easy, right? Instead of doing parallel axis shift to figure out my composite moment of inertia about O, hey, these guys are just about their CGs. So this and this, easy. Very, very simple to write. It's just flip to your back of your book, a rod about its CG, 1/12 ml squared. Done. Where you got to pay the price a little bit is that these two terms, we have to track their velocities. We need to find these in terms of omega. So we need to figure out how fast is the CG going. So my V1, it's on a circular path. My V2, it's on a circular path. So V1, its velocity is omega times the distance, L over 2. My V2, omega times its distance. That distance, remember, was this funny little triangle. L squared plus L over 2 squared, square rooted. Oh. My brain says, hey, instead of tracking 4 terms and having to track them at state 1 and then again at state 2, now I'm going to prefer to make a composite moment of inertia for the system. And then I just have to track 1 term. 1 term at state 1, 1 term at state 2. Less places to screw up. That's it. You're free to do it however you choose, though. All right. So moving on, forces and moments on a rigid body. Remember, just like last time where we took out our spring conservative forces from the work term, we took out gravitational forces, and we made potential energy terms. we can read these slides and go through, but the idea is that, hey, none of that changes. So if we think of our work as the integral of F dotted with our distance, conservative forces, we pulled out gravity. We said this was just mgh. We called this potential energy. Remember, the key for potential energy was maybe I have a system of beams and bars and whatever. I pick my datum. I'm going to track this. Maybe this is going to be my state 1. When it comes down to here, this will be my state 2. Hey, I've moved down. So I just have to have my G, or my H, be negative on the 2 term because I've moved down in potential. So potential energy, it doesn't change. The only gotcha is that before we just said mgh. Now this h, we have to track the CG location of our body. Because we might have a rigid body that can rotate, like this blob that we're showing in the figure here. Hey, it can spin all at once, but as long as I know how high up and down the center of gravity moved, that's all I got to do for potential energy. So this term, unchanged. Springs, still the same, half kx squared. The one gotcha is that for our work, here we were looking purely at translations, forces dotted with displacement. We could also use moments now. Now that we have a body rotating, we can put torques on these bodies. So work can also be the integral of moment dotted with d theta. And think like, hey, those units make sense. I got force times distance, Newton meters. Here I've got moment, Newton meters, and theta, which is kind of our junk variable, right? Radians don't come along. So again, this is going to end up being Newton meters. I could get a little trickier and say, hey, this is also moment dotted with omega dt. Because omega is d theta dt, right? So that would be sneaky if I did that to you on the final, where I said, hey, these problems are all about speed and position. And then I threw in a little time variable to mess with you. No, I won't do that, I promise. But I could. I could. All right. Last point. Friction, roll without slip. I think we even talked about this for when we were doing particles. If I've got this body and it's moving along, I've got some friction acting on my ground at point S here. Here's our friction. But if we're rolling without slip, this force is acting over zero displacement because the point at which it's in contact with the ground isn't translating relative to the ground. So there's no relative motion between the ground and the bottom of our wheel at any given time. So if there's no relative motion, the force is acting over no distance. So my F dotted with dr, there is no dr, right? There's no change in position. So the gotcha here, if and only if this is a roll without slip condition, I've got no translation here at this point. I've just drawn at the bottom, so no work. But if I got some external pushing or pulling force P, hey, that is operating over some distance, right? Maybe it's going out that far. So that one could give us work. Or if I've got a torque on the wheel. My motor is providing a torque. Hey, that's a torque acting over some angle theta. That's going to be an external work term that we need to track along. So static friction, don't worry. Kinetic friction, if we're sliding, then we got to worry. Torsional springs, I forgot you were in there. Last thing, torsional springs. Velocity of a spring from torsion, or velocity. Potential energy of a spring from torsion. So, if we think to what a linear spring was, linear spring, we got the force from a spring, kx. We're going to integrate that over distance dr, right? A torsional spring, this is going to create a moment. And our moment, k torsion, times theta. And apparently I got a negative sign in here because it's going to be a restoring moment. Whichever way you turn this thing, it's going to want to go back the other direction, right? So if we do this, and we look at our work as an integral of m dotted with d theta, from this we're going to find that our kinetic or potential energy from a torsional spring, much like we got from the kinetic energy of a linear spring, of half k delta squared, or kx squared. Now this is just going to be half k torsional theta squared. Very, very similar. That, hey, if I got a spring and I stretch it, or if I compress it, I don't really care. My energy is still going to be stored in that spring, just based on delta squared. Torsional spring, the same thing. Whether my torsional spring, I pull it one way and store energy, or I pull it the other way and store energy, that theta being positive or negative is going to work its way out. I'm just storing energy in the spring. So my potential, kt times theta squared, half kt theta squared. That is pretty much the same thing we did before. Okay, now I think I'm done. All right, one big problem, and we'll get out of here. So we've got this drum with a big mass B hanging from it. So we've got this mass. This drum is pinned at its center. And the drum has a mass of 50 kilograms and a radius of gyration about 0.0 of 0.23 meters. If the 15 kilogram block B is moving downwards at 3 meters per second, so this guy is 3, and it's going down. We've got this big brake arm at P that we're pushing against the drum. And there's going to be some frictional force between the drum and this arm. So we're going to push with 100 newtons. And we want to figure out how far do we go before that brake stops, or the block stops. So how far down is block B going to drop before it comes to a stop? And we're given a friction coefficient to use on our bar. So how far down are we going? D. My rope isn't on the outside of this drum. It's at some inner radius. And this thing is 15 kilograms, I think. I want to know how far down it goes. This is my D variable. R inner, 0.15 meters. And what's happening on the other side here? I got this arm. I'm going to draw it out a little bit. I'm pushing on this thing with some force P. And then what's going on here? I've got this disc rotating this way. So I've got a normal force acting between these two guys. And I've got a frictional force trying its hardest to slow this thing down. So it's acting down on the drum, and I guess it would be acting up then on the bar. That's kind of what our system looks like. So if we do this, I got this thing rotating. This frictional force is going to create a moment. So at some point, we're going to need to relate my distance d and our angle theta together. Since this pulley or this mass is wrapped around at a given radius, shouldn't be too hard for us to relate how far it goes down with how much it's rotated. Angle theta. So let's look at our work energy and start trying to pluck off the various terms. T1, V1, plus work, non-conservative, T2 plus V2. Okay. This is just our generic starting point, right, for all these work energy problems. State 1, we're moving at 3 meters per second down. State 2, we're stopped. So I like that one. That T2 goes away. For my potential, I've got gravity and I've got springs. I don't see any springs in here, but I do see gravity. So my drum isn't going to move up or down, but my mass is going to move up and down. So that one we have to take into account. If we set our initial height as our datum, we can let V1 go away. V2 then, mass of the block, MB, times G, times D. Our distance, but we're going down, so we're losing energy, potentially. So, minus that distance D down. That term is accounted for. T1, we got this thing moving. Well, I've got my mass, half mb vb squared. That thing is translating. If you kind of think about its motion, it's just going straight up and down. So you don't have to worry about rotation on that. But in order for this guy to go up and down, that drum needs to rotate. Plus the energy from the drum. Well, that drum, half, it's pinned, so we can use IO, pinned about O, times omega squared. Here, we got to relate VB and omega. So this point on B is 3 meters per second. So if I climb my way back up the rope, this point on the disk is doing the same thing. These guys are moving together right? So my velocity is related to my angular velocity. V is just going to be equal to omega times r, r being the inner radius. So we want to get rid of omega here because I know I'm given v. So omega is just v over r sub I. This is me going pretty fast. Right? If you didn't like going fast here, you can go slow, right? Hey, I call this point O, and I call this, let's call that point A. My velocity at A is equal to my velocity at O plus omega cross the vector between them. O is pinned. Omega cross r. It's this little guy. I just took it a little quicker, right? So we've got omega. Good. Still got a little bit of work to do. My moment of inertia about point L. I've got the radius of gyration given in the problem statement. And to use that, we're given that K sub O is 0.23 meters. So given a radius of gyration, maybe you don't have a regular shape. Maybe this is a drum with some wire wrapped around it. So instead of trying to figure out the composite system of all these different pieces added together, maybe the problem statement will give you a radius of gyration. So if you have a radius of gyration, the moment of inertia is just mass times that radius squared. This is essentially saying that if we've got our point O here, no matter what this blob looks like, I'm just going to pretend like all of its mass is at a distance K sub O from the center line. And then how do I find the moment of inertia about a point mass about a point? Mass times that distance squared. So this is just a shorthand way for us to say, hey, how is that mass distributed relative to point L? Radius of gyration. And then I use that with mass times radius of gyration squared. We have seen that come up a few times. So our kinetic energy, this one we've got now, half mb, 15 kilograms. Velocity of b, 3 meters per second squared. Plus my rotational term, half I sub O. That's this guy. Nope, I know it now. It's 50 kg times 0.23 meters. That term is squared. And my omega, it's my velocity divided by r. So my velocity is 3 meters per second. My inner radius was 0.15 meters. That term squared. So my kinetic energy, 596.5 Newton meters. Okay. This is a decent start. I got 1 minute left. I'm going to finish this later. But the term that I need to come up with is the work term. So the non-conservative work term, I need to figure out what this frictional force is. And this is going to be the moment dotted with my change in rotation theta. So I will work this piece out, and I will attach it to the back here to show you what the answer is to finish it off. But this is what I got, and I got to get it from my bar.